Class 11th, Subject Physics, 6th Chapter, Mechanical Properties of Solids. Mechanical Properties of Solids. From this chapter, let us see numericals from exercise. Numericals from exercise. Let us see numerical number 1, which is stated as calculate the coefficient of static friction for an object of mass 50 kg placed on horizontal table pulled by attaching a spring balance. The force is increased gradually and it is observed that the object just moves when spring balance shows 50 Newton. And therefore, for this numerical number 1, the given data is mass m1 equal to 50 kg, acceleration due to gravity g equal to 9.8 meter per second square, the force F is equal to 50 Newton, and we have to calculate the coefficient of static friction mu s. Now the force of static friction is given as Fs equal to mu s into n. Fs is equal to mu s into n, but n is equal to mg, and therefore Fs will be equal to mu s into mg, mu s into mg, and therefore coefficient of static friction mu s will be equal to Fs upon mg, Fs upon mg. Putting the values, we will get 50 upon 50 into 9.8, 50 upon 50 into 9.8, 50 will get cancelled, and we will get 1 upon 9.8, whose value comes out to be 0.102, 0.102, and this will be the coefficient of static friction. Then let us go for numerical number 2, which is given as a block of mass 37 kg rests on a rough horizontal plane having coefficient of static friction 0.3. Find out the least force required to just move the block horizontally. And therefore, for this numerical number 2, the given data is m is equal to 37 kg, then mu s equal to 0.3, acceleration due to gravity g equal to 9.8 meter per second square, and we have to find out the least force to move that block just, and therefore it is the force for static friction, that is force of static friction Fs, we have to calculate. Now we know the formula for force of static friction Fs equal to mu s into mg, mu s equal to mg, and therefore from this we can write 0.3 into 37 into 9.8, 0.3 into 37 into 9.8, that comes out to be 108.8 Newton. 108.8 Newton, that will be the force of static friction. Then we will go for numerical number 3, and which is stated as a body of mass 37 kg rests on a rough horizontal surface. The minimum horizontal force required to just start the motion is 68.5 Newton. In order to keep the body moving with constant velocity, a force of 43 Newton is needed. Then what is the value of coefficient of static friction and coefficient of kinetic friction? And therefore for this numerical number 3, the given data is mass of the block m is equal to 37 kg, force of static friction Fs equal to 68.5 Newton, then force of kinetic friction Fk equal to 43 Newton. Acceleration due to gravity g equal to 9.8 meter per second square, and we have to find out coefficient of static friction mu s and coefficient of kinetic friction mu k. We know the formula for coefficient of static friction mu s equal to Fs upon mg. Fs upon mg. Then putting the values we will get 68.5 upon 37 into 9.8. That comes out to be 0.1889. 0.1889, and this will be the value of coefficient of static friction. Now for coefficient of kinetic friction, we have the formula Fk upon mg. Fk upon mg. Putting the values we will get 43 upon 37 into 9.8. 43 upon 37 into 9.8, which comes out to be 0.1186. 0.1186, and this will be the value of coefficient of kinetic friction. Then we will go for numerical number 4, which is given as a wire gets stretched by 4 mm due to a certain load. If the same load is applied to a wire of same material with half the length and double the diameter of the first wire, then what will be the change in its length? And therefore for this numerical number 4, the given data is delta L1 is equal to 4 mm, then L2 is equal to L1 by 2, L2 is equal to L1 by 2, diameter D2 is equal to 2D1, D2 is equal to 2D1, as D2 is equal to 2D1, therefore same ratio will be for radius, and therefore R2 is equal to 2R1. R2 is equal to 2R1, and we have to find out delta L2. Delta L2. And therefore in the solution we can say that as load F, load applied F, and the material is the same, therefore Young's modulus Y both are the same, that is applied load F and Young's modulus Y both are same for these two wires, and therefore as Young's modulus Y is equal to FL upon A into delta L, that is pi R square into delta L. Y will be equal to FL upon A into delta L, but here A will be pi R square. From this, delta L change in length will be equal to FL upon pi R square Y. Delta L is equal to FL upon pi R square Y, and therefore for delta L1 and delta L2 we can write the expression as delta L1 equal to FL1 upon pi R1 square Y. FL1 upon pi R1 square Y, and delta L2 will be equal to FL2 upon pi R2 square Y. FL2 upon pi R2 square Y. Now taking the ratio of delta L2 to delta L1, we will get delta L2 upon delta L1 is equal to FL2 upon pi R2 square Y divided by FL1 upon pi R1 square Y. Now this ratio will be written in the form of product as FL2 upon pi R2 square Y into reciprocal of this, that is pi R1 square Y upon FL1. Pi R1 square Y upon FL1. F are same, therefore we will get cancelled. Then pi and Y will get cancelled, and therefore we will get delta L2 upon delta L1 as L2 by L1 into R1 square by R2 square. L2 by L1 into R1 square by R2 square, and therefore that will be equal to L2 by L1 is equal to half, since L2 is equal to L1 by 2 and therefore L2 by L1 will be equal to half. Similarly, R1 square by R2 square will be equal to half square, because R1 by R2, this R1 by R2 will be again half and its square is there, and therefore we will get half into half square, that will be equal to half into 1 by 4, which comes out to be 1 by 8. So delta L2 upon delta L1 equal to 1 by 8, and therefore we can write delta L2 equal to delta L1 into 1 by 8. But delta L1 is equal to 4 mm, so that 4 into 1 by 8, that will be equal to 1 by 2, which will be equal to 0.5 mm. So this will represent delta L2. So value of delta L2 comes out to be 0.5 mm. Then we will go for next numerical, that is numerical number 5, which is stated as calculate the work done in stretching a steel wire of length 2 meter and cross-sectional area 0.0225 millimeters square. When a load of 100 Newton is slowly applied to its free end, given that Young's modulus of steel is 2 into 10 raised to 11 Newton per meter square, and therefore for this numerical given data is L is equal to 2 meter, L is equal to 2 meter, force F equal to 100 Newton, then area of cross section of the wire is A equal to 0.0225 millimeter square, which will be written as 0.0225 into 10 raised to minus 6 meter square, that will be equal to 2.25 into 10 raised to minus 8 meter square. So this will be the area of cross section, and Young's modulus Y is equal to 2 into 10 raised to 11 Newton per meter square, and we have to find out the work done W. Now we know the formula for work done in stretching that wire, that is W is equal to half F into delta L, half F into delta L, but as Young's modulus Y is equal to FL upon A into delta L, Y is equal to FL upon A into delta L, therefore delta L will be written as FL upon AY. Delta L is equal to FL upon AY. Putting value of delta L in the formula of work done, we will get W is equal to half F into FL upon AY, FL upon AY, which will be further written as F square L upon 2AY, F square L upon 2AY, because F into F is there, so that F square L upon this 2AY we will get. Now putting the values, we will get 100 square into 2, 100 square into 2 divided by 2 into 2.25 into 10 raised to minus 8 into 2 into 10 raised to 11. 100 square into 2 divided by 2 into 2.25 into 10 raised to minus 8 into 2 into 10 raised to 11. Simplifying this, we will get W is equal to 20 upon 4 into 2.25. 20 upon 4 into 2.25, which comes out to be 20 upon 9. 20 upon 9, which will be equal to 2.222 joule. 2.222 joule. This will be the work done. And then we will go for next numerical, that is numerical number 6. And for this numerical number 6, it is given that a solid metal sphere of volume 0.31 meter cube is dropped in an ocean where water pressure is 2 into 10 raised to 7 Newton per meter square. Then calculate the change in volume of the sphere if bulk modulus of that metal is 6.1 into 10 raised to 10 Newton per meter square. And therefore, for this numerical, the given data is volume V is equal to 0.31 meter cube. Then P is equal to pressure P equal to 2 into 10 raised to 7 Newton per meter square. K is equal to so K, that is nothing but the constant, which will be equal to 6.1 into 10 raised to 10 Newton per meter square. K is equal to 6.1 into 10 raised to 10 Newton per meter square, and that K is nothing but that bulk modulus. Bulk modulus K will be equal to 6.1 into 10 raised to 10 Newton per meter square, and we have to find out change in volume delta V. So the bulk modulus K will be equal to minus P upon delta V upon V. K is equal to minus P upon delta V upon V, which will be equal to minus PV upon delta V. Minus PV upon delta V, this V will be shifted to numerator. And therefore we will get delta V equal to minus PV upon K. Delta V equal to minus PV upon K. Now putting the values, we will get delta V equal to minus 2 into 10 raised to 7 into 0.31 divided by 6.1 into 10 raised to 10. Solving this, we will get minus 0.62 upon 6.1 into 10 raised to minus 3, and therefore delta V will be equal to minus 0.1016 into 10 raised to minus 3, which comes out to be minus 1.016 into 10 raised to minus 4, minus 1.016 into 10 raised to minus 4 meter cube. This negative sign will indicate that there will be decrease in volume. And then we will go for next numerical, that is numerical number 7, which is given as a wire of mild steel has initial length 1.5 meter and diameter 0.60, that is 0.60 millimeter, gets extended by 6.3 mm. Extension of the wire is 6.3 mm when a certain force is applied to it. If Young's modulus of mild steel is 2.1 into 10 raised to 11 Newton per meter square, then calculate the force applied. And therefore, in order to calculate that force applied, let us see first of all the given data. Length of the wire is 1.5 meter. Then diameter of the wire is 0.60 millimeter. Then delta L, that is change in length, equal to 6.3 millimeter, which will be equal to 6.3 into 10 raised to minus 3 meter. Now in this case diameter D is 0.60 millimeter, therefore radius will be 0.30 millimeter, and then it will be converted into meter by multiplying by 10 raised to minus 3, and therefore Y is given again, that is 2.1 into 10 raised to 11 Newton per meter square. Y is equal to 2.1 into 10 raised to 11 Newton per meter square, and we have to calculate force applied. F is equal to question mark. Therefore, we are having the formula for Young's modulus, that is Y is equal to FL upon A into delta L. Y is equal to FL upon A into delta L, and therefore we can write F equal to YA delta L upon L. YA delta L upon L, which will be written as Y. A will be equal to pi r square into delta L upon L. So Y into pi r square delta L upon L. Putting the values, we will get F is equal to 2.1 into 10 raised to 11 into 3.142 into 3 into 10 raised to minus 4 square, that is r square. 3 into 10 raised to minus 4, it is value of r in terms of meter, into 6.3 into 10 raised to minus 3. 6.3 into 10 raised to minus 3 divided by length L, that is 1.5. By solving this, we will get 2.1 into 3.142 into 9 into 6.3, 9 into 6.3 upon 1.5. By solving this, we will get 249.4 Newton. 249.4 Newton, approximately it will be equal to 250 Newton. 250 Newton. So this will be the force required.